There is a drill bit that hit 900 degrees Celsius and kept going. Not a simulation, not a controlled experiment. A real drill bit on a real rig in northeast Iceland in 2009. The plan was to reach 4.5 kilometers depth. The bit reached 2.1 kilometers and stopped. Not because of equipment failure, because molten rock flowed up into the borehole. The magma found the hole before the drill, found the magma. The engineers had two choices: abandon the well, or figure out what they had accidentally discovered. They chose to figure it out. What they found was remarkable. The magma chamber, sitting 2 kilometers below Krafla volcano, was surrounded by superheated rock. Temperatures there approached 500 degrees Celsius. That rock had been fractured by the drilling fluid used during the accident. The fractured rock was now permeable. A pathway for steam had opened that had never existed before. The accidental magma contact achieved something remarkable. Decades of careful geological planning had never achieved it. It created a connection to the deepest, hottest, most energy-dense geothermal resource on the planet. The well they planned to drill would have produced roughly 5 megawatts of electricity. The accidental magma well produced 30 to 40 megawatts instead. That came from a single borehole. Iceland has a population of 370,000 people. The country is already powered entirely by renewable energy. Iceland looked at what it had accidentally discovered. Then it decided to do it again, on purpose. Deeper, hotter, with a clear understanding of what supercritical conditions could mean. They could reshape the energy future of the entire planet. This is the story of what Iceland found when it drilled into magma by accident, and what it has been trying to do with that discovery ever since. The Iceland Deep Drilling Project started in 2000. 25 years of drilling, failing, learning, and drilling again. It is chasing an energy source that could be described, without exaggeration, as unlimited. The closest thing to unlimited heat that the planet provides near the surface. The magma that drives Iceland's volcanoes is the same magma. It could, if the engineering works, drive turbines that heat buildings across Europe. To understand why supercritical conditions change everything, consider this. You need to understand what normally limits geothermal energy. A standard geothermal well in Iceland reaches roughly 2 to 2.5 kilometers depth. At that depth, the rock is hot enough to boil water. The steam that rises through the well drives a turbine. That turbine generates electricity. Standard, reliable, clean. Iceland has been doing this for decades. The limitation is temperature. At 2.5 kilometers, Iceland's rock temperature reaches roughly 250 degrees. It can climb to 300 degrees Celsius. That is hot enough for good steam generation. It is not hot enough for supercritical conditions. Water behaves differently under extreme temperature and pressure. Above 374 degrees Celsius and 220 atmospheres of pressure, water changes. It stops being either liquid or steam. It enters a supercritical state instead. That is a phase of matter with a liquid's density and a gas's viscosity. Supercritical water is an extraordinarily efficient energy carrier. It holds far more thermal energy per cubic meter than conventional steam. A well-producing supercritical fluid from a deep hot reservoir does more than generate extra electricity. It generates fundamentally more. A supercritical well above 450 degrees could yield 10 times the output. That compares to a conventional geothermal well at the same flow rate, 10 times. One supercritical geothermal well could replace 10 conventional wells. That requires drilling to 4 or 5 kilometers instead of 2 to 2.5. Those rock formations are hard to drill through and hostile to equipment. But if you can drill there and produce from there, the economics transform entirely. Iceland drilled there accidentally in 2009. Then it drilled there deliberately in 2016 and 17. The second well reached 4.6 kilometers. Temperature at that depth measured 426 degrees Celsius. Estimated formation temperature at the bottom ranged from 500 to 600 degrees. Supercritical conditions confirmed. Here is why Iceland is the only place on Earth where this is possible right now. Iceland sits directly on the mid-Atlantic ridge. The North American and Eurasian tectonic plates pull apart there. They separate at roughly 2.5 centimeters per year. Magma from the Earth's mantle rises continuously into the gap. Iceland is essentially a volcanic island continuously being created by the planet's interior. The geothermal heat under Iceland is not residual heat from ancient geological events. It is active heat from magma injected into the shallow crust within living memory. The Krafla volcano, where the first Iceland Deep Drilling Project well was sited, had a volcanic episode. That happened as recently as 1984. The magma the drill hit in 2009 was fresh, recently emplaced, geologically speaking, still warm from its journey upward. The depth for supercritical conditions varies dramatically by geology. In continental interiors, far from tectonic activity, reaching supercritical temperatures requires drilling 8 to 10 kilometers or deeper. The drilling technology to reach those depths economically does not currently exist. In Iceland, supercritical conditions occur at 4 to 5 kilometers. That is a depth existing drilling technology can reach. Difficult, expensive, requiring specially engineered casing and fluid systems, but achievable. The Iceland Deep Drilling Project proved it achievable. The project began with a simple observation. Iceland's shallow geothermal systems are fed by heat from deep magmatic intrusions. Drilling into those deeper heat sources directly could access energy densities shallow systems cannot reach. The geology of Iceland makes this a physics problem rather than a pure economics problem. The heat is there, close enough to the surface. It sits in rock, permeable enough to allow fluid flow. The question was whether drilling technology could keep pace with the geology. 2 wells and 25 years of research later, the answer is yes. With significant caveats. Here is the engineering nightmare the IDDP-2 well documented. It happened in 2016 and 17. The second Iceland Deep Drilling Project well was drilled at Reykjanes. That sits on the Reykjanes Peninsula in southwest Iceland. The site sits on the landward extension of the mid-Atlantic ridge. The geothermal fluid at Reykjanes is modified seawater. It circulated through the submarine ridge system before emerging on land. The well reached 4.6 kilometers depth. It measured supercritical conditions. It recovered core samples from the bottom section. These were genuine firsts. It was the deepest and hottest drill hole on an active mid-ocean spreading center. It was also the first penetration of an active supercritical hydrothermal environment. That depth is comparable to the reaction zones feeding black smoke events. Then, the casing failed. The production casing could not withstand the sustained conditions at 4.6 kilometers. That meant 240 bar of supercritical fluid. The steel tube allowing controlled fluid production to the surface failed. Thermal expansion, corrosion from hot saline fluid, mechanical stress at the edge of engineering capability. Combined, they made the production section of the well inaccessible. The well that proved supercritical conditions were reachable, could not produce from them. This is the central engineering challenge of deep geothermal. The physics confirms the energy is there. The chemistry of the fluid at supercritical conditions attacks conventional materials. Stainless steel corrodes. Standard casing alloys fail. Equipment that works at 2 kilometers in conventional geothermal wells fails at 4 to 5 kilometers. Supercritical environments break it. Norwegian researchers at SINTEF Materials and Chemistry identified the showstopper explicitly. Drilling long-reach wells in hard rock formations is costly. Materials must also survive extreme temperature, pressure, and corrosive fluids simultaneously. That combination is what stands between the confirmed resource and commercial production. The IDDP-2 failure was not a scientific failure. It was an engineering boundary condition. The next project must solve the casing. Here is what IDDP-3 is designed to do differently and why it matters. The third well of the Iceland Deep Drilling Project is planned for the Hengill area. That area sits in southwest Iceland. Hengill is one of Iceland's most geothermally active regions. Reykjavik's district heating system draws from Hengill. Conventional geothermal power plants already operate there. The deep system beneath those plants is the target. Evidence of superhot formations at approximately 2 kilometers depth at Hengill is documented. The geological gradient is better understood at Hengill than at previous sites. Lessons from the first 2 IDDP wells shaped the planning. Both wells informed how IDDP-3 is designed. The casing failure that ended IDDP-2's production phase is the primary target. Materials capable of surviving supercritical saline fluid at 4 kilometers depth are the research priority. They must survive years of sustained production. The Flowfius program has developed a revolutionary drilling technique. It cuts through hard crystalline bedrock, funded through Horizon Europe. It is faster than conventional rotary drilling. It is cheaper per meter drilled. It applies directly to Iceland's deep basement rock challenge. Titanium alloy casing systems are under development. Ceramic composite materials are being tested for the most extreme sections. High-temperature packers and seals aim to hold integrity at supercritical temperatures. The engineering roadmap from IDDP-2's failure to a viable well is not yet solved. But it is defined. The problems are known. The research directions are active. The funding is in place. IDDP-3 is not a repeat of what failed. It is the engineering response to what failed. The IDDP-3 planning process is the most detailed yet. No previous IDDP well received this much preparation. Failures from the previous 2 wells are documented in granular engineering detail. That includes the casing failure modes. It includes the fluid chemistry that attacked the steel. It includes the temperature cycling that caused differential expansion. Each failure mode now has a proposed engineering response. Whether those responses are adequate is the open question. The only way to find out is to drill. Here is what success at IDDP-3 would mean for Iceland and for the global energy transition. Iceland is already 100% powered by renewable energy. Hydroelectric and geothermal together supply all of the country's electricity. Iceland does not have a fossil fuel dependency problem to solve. Iceland has a different problem. It has more renewable energy than it knows what to do with. That is true even at its current scale. The geothermal resource under Iceland is essentially unlimited. That is compared to Iceland's population of 370,000 people. The country has been exporting electricity-intensive industries, primarily aluminum smelting. The electricity is too cheap and too abundant to use only domestically. A successful supercritical well changes the economics of Icelandic energy in a specific way. A single well could produce 30 to 40 megawatts instead of 3 to 4. That reduces the surface footprint of geothermal infrastructure per unit of energy. Less surface disturbance, less land use. Fewer conventional wells are needed to achieve the same output. For the global picture, success at IDDP-3 would provide something valuable, an engineering blueprint for supercritical geothermal where the physics is most favorable. The casing materials and drilling techniques developed for Iceland's wells would be evaluated elsewhere. Other volcanic regions could apply them next: the Philippines, Japan, Kenya, New Zealand, Indonesia. These countries sit on active volcanic systems with supercritical conditions at accessible depths. Beyond volcanic regions, the longer-term vision is enhanced geothermal systems in non-volcanic terrain. Places where the heat sits deeper, where the rock must be fractured artificially rather than relying on natural permeability. Where drilling to 6 or 7 kilometers is required instead of 4 to 5. That application is decades away, even if IDDP3 succeeds. But IDDP3's success is the first step on that path. Here is the honest assessment of where the project actually stands. The Iceland Deep Drilling Project has confirmed supercritical conditions at reachable depths. This is a genuine scientific achievement. The physics of the resource is not in doubt. No supercritical geothermal well has produced electricity commercially anywhere in the world. Not in Iceland, not anywhere. The first IDDP well produced steam, but had its casing damaged. The second IDDP well confirmed supercritical conditions, but could not produce from them. Both wells identified the resource. Neither has delivered the commercial product. The 10 times power output figure is a modeling estimate based on reservoir physics. It assumes a well that can produce supercritical fluid at sufficient flow rates. It must also sustain that production over the years commercial operation requires. A well that fails its casing in the first months does not produce 10 times anything. The material science challenges are real and unsolved. Titanium alloys and ceramic composites are expensive. Drilling at 4 to 5 kilometers in hard granite costs far more per meter. That exceeds the cost of conventional geothermal wells by a significant margin. A well producing 10 times the electricity but costing 15 times as much to drill. That does not automatically produce a better business case. IDDP3 is in planning. Funding is being assembled. The drilling timeline has not been publicly confirmed with a specific date. The project timeline has historically run longer than initially announced. The resource is real. The engineering pathway is defined. Commercial production from supercritical wells remains undemonstrated. That gap between confirmed physics and commercial reality is what IDDP3 targets. Whether it closes that gap is the most important unanswered question in deep geothermal. Here is the geopolitical dimension that transforms an Icelandic science project into a global strategic story. Europe imports approximately 400 billion cubic meters of natural gas per year. The Russian gas supply disruption that began in 2022 exposed something critical. European energy security depends on gas supplies that can be politically interrupted. The response has been a massive acceleration of European renewable energy development. Offshore wind, solar, nuclear restarts, hydrogen. All of these receive enormous investment and political attention. Deep geothermal in volcanic regions receives far less attention. But it offers something wind and solar cannot: firm baseload power. That means generation running continuously, regardless of weather, time of day, or season. 24 hours per day, 365 days per year. Picture a Europe that heats buildings and generates baseload electricity from deep geothermal. Sources in Iceland, the Azores, the Canary Islands, and Italy's Campania region. That Europe would not need gas pipelines from politically unreliable sources. The question is whether the engineering can be solved on a timeline that matters. European energy security policy needs answers now. The Russian gas disruption created urgency in 2022. Policy decisions about energy infrastructure take years to implement. A technology needing another decade of research cannot solve today's budget cycle problem. This is the fundamental tension in deep geothermal energy. The physics confirms the resource. The politics creates the urgency. The engineering timeline sits between them. Iceland's IDDP project is the only program that has actually drilled to supercritical conditions. It is the only one that has measured the result. Everything else in deep geothermal is modeling, planning, or shallower conventional geothermal. If the engineering gap is closed in Iceland, the implications extend far beyond a small island. They reach across the North Atlantic and beyond. Here is the volcanic geology context that explains why this story starts and ends in Iceland. The Mid-Atlantic Ridge is a mountain range running the length of the Atlantic Ocean floor. It stretches 16,000 kilometers long. It rises 3 kilometers above the surrounding ocean floor. It is the boundary where the Atlantic Ocean is being created. Spreading plates and upwelling magma drive that creation. Iceland is the only place on Earth where this ridge rises above the ocean surface. Ridge spreading and a mantle hotspot beneath Iceland combine. Together they produce an anomalously high magma flux. The island is geologically young, active, and extraordinary. Beneath Krafla, Reykjanes, and Hengill, magmatic intrusions sit at 2 to 5 kilometers depth. These are the heat sources for Iceland's conventional geothermal power. They are also the targets of the deep drilling program. The first IDDP well at Krafla did not find ancient residual heat. It found magma emplaced within the past few decades, hot enough to flow, fluid enough to enter the borehole. It was recent enough that surrounding rock stayed at extreme temperatures. Those are the temperatures supercritical geothermal requires. This geological luck, fresh magmatic heat at shallow depth, does not exist in most of the world. In continental interiors, far from tectonic boundaries, the Earth's heat is older and deeper. The gradient to supercritical temperatures there requires drilling 2 to 3 times as deep. Iceland is the geological laboratory for supercritical geothermal because the physics is most accessible there. Engineering solutions developed in Iceland will then be scaled and adapted, first to other volcanic regions. Eventually, if the technology matures, to most of the planet's surface above older, deeper heat. But the laboratory is in Iceland, and the laboratory is still running its experiments. Here is the broader deep geothermal landscape that puts Iceland's project in context. The United States Department of Energy funded a program called Frontier Observatory for Research in Geothermal Energy. Its primary site in Nevada has drilled wells to nearly 3 kilometers. That is in non-volcanic terrain. The program tries to create artificial permeability in hot, dry rock. It uses hydraulic fracturing, essentially the same technique used in oil and gas. The early results have been mixed. Creating fractures is achievable. Sustaining fluid flow through those fractures at commercial rates has proved difficult. In Australia, Geodynamics Limited spent over a decade on a similar effort. It tried to develop enhanced geothermal systems in the Cooper Basin's hot, dry rock. The geological heat there is genuine. The engineering to extract it commercially has not been demonstrated at viable cost. In France, the Sulz 4T enhanced geothermal plant has operated since 2016. It runs in the Rhine-Graben at 1.5 megawatts. That is a proof of concept, not a commercial-scale demonstration. The pattern across all these programs is consistent. Deep geothermal resources are confirmed everywhere researchers have looked. Commercial production at competitive cost has not been demonstrated, not outside of Iceland's conventional volcanic geothermal systems. Iceland's IDDP program is the most advanced attempt to close this gap. Not because Iceland has better engineers, because Iceland has better geology. The supercritical resource at 4 to 5 kilometers is accessible there with current technology. Equivalent resources elsewhere require technology that does not yet exist. Iceland's geological advantage is not transferable, but the engineering solutions developed to exploit it are transferable. That is why IDDP-3 matters beyond Iceland. It matters for every country sitting above deep thermal resources current drilling cannot reach. Here is the full picture of what Iceland discovered, and what it has proven, and what remains to be done. In 2009, a drill bit at Krafla volcano hit magma. That happened at 2.1 kilometers depth. The planned well became something no one had engineered. The unexpected magma contact created a working geothermal well. It produced 30 to 40 megawatts from a single borehole. That is 10 times the output of a conventional Icelandic well. The accidental discovery proved supercritical geothermal resources were reachable. In 2016 and 17, Iceland drilled to 4.6 kilometers at Reykjanes. It measured rock temperatures of 500 to 600 degrees Celsius. It confirmed supercritical conditions. It recovered core samples from the deepest, hottest drill hole on an active spreading center. Then the casing failed, and the production section became inaccessible. The resource is confirmed. The engineering is not yet solved. Materials that can survive supercritical conditions for years do not yet exist affordably. IDDP-3 at Hengill is the next experiment. It will apply 25 years of IDDP lessons. It aims to produce electricity from a supercritical well for the first time. One well producing 40 megawatts instead of 4. If the engineering holds, if the casing survives, if the flow rates justify the cost, the physics says 10 times the energy per well. The engineering says not yet. The gap between those two statements is what IDDP-3 is built to close. Iceland drilled into magma by accident in 2009. It drilled into supercritical conditions on purpose in 2016. It is planning to produce electricity from those conditions next. The energy under Iceland has been building for millions of years. It is the same energy driving the island's volcanoes, geysers, and hot springs. That has been true since long before anyone drilled into it. The difference now is that someone is trying to turn that heat into electricity. They aim for densities no previous technology has achieved. If it works, the deepest hot rock under Iceland becomes something extraordinary. The most energy-dense renewable source on Earth. Per well, per surface footprint, per megawatt of output. The drill is going back down. Drop your answer below. Can deep geothermal actually replace natural gas for European energy security?